So formal charge is our way to tell structures apart and decide which one is most likely to be found in the real world. So a lot of times you'll hear us say, oh, this is good. It has good formal charges. This is the good structure. This is the better structure. And what we mean is most likely to be to match what's real. We have these little mathy rules, these little mathy tricks. It seems like a really simple formula, seems kind of silly, but it seems to be what tells us which structure is best. So I'm actually going to jump to this section, and then I'm going to go back up to the top, and we're going to work with the formulas. So here's what's best when you come up with a situation where all the formal charges are zero. So that's your goal. Your goal is to have a structure where everything is zero. Now, sometimes it just doesn't work out, and the atoms will still bond up if you've got some things that aren't zero with a formal charge, and it doesn't anyways, so it's okay with it. But you want the lowest numbers to be +1 or -1. You don't want to like 2s or 3s or -2s or -3s. That's really, really bad. Those are the two main rules. If between those two you can't get it rolled down, and in general chemistry you probably will be able to, there's two more little rules. If you end up with atoms beside each other, so like that's beside each other, they're bonded, right? So if you have them beside each other and both of them have a formal charge, one should be positive, one should be negative, just FYI. And then if you still have that situation and you still can't figure out, then the negative one of that group should be on the more electronegative atom. So those last two rules aren't such a big deal. The first two really big deals in general chemistry. So let's go back up to the top. And a little note is you'll see a little funny thing coming up where the central atom is the third row or lower, and formal charge is going to let us get to the structure that actually exists in real life. So formal charge of an atom is the hypothetical charge the atom would have if we would distributed the electrons in the bond evenly between the atoms. It's not the actual charge. It's not a real thing at all. Like it's not a real charge at all. It's like record keeping or bookkeeping, except that it just works. It works. So we've got two versions of a formula. I'm going to show you both versions because there's a possibility if you're taking Orgo and your Orgo teacher wants you to use the formula. I'm just letting you know there is a faster way than this formula. On the chart, on the periodic chart, we're going to be using valence electrons. You've already done a ton. Hopefully you have not forgotten them, but pretend that this is a little periodic chart here. So remember, it's the first tall column, second tall column, third, fourth, fifth, sixth, seventh, eighth. So if like your boron and you're here, you have 3 valence electrons. So do you remember that? Or like if you're chlorine, you're over there, you've got 7. So valence, that's just how many you've got. So in the case of boron, I'm going to fill this out. So for boron's formal charge, I have 3 minus, and sometimes this is also called non-bonding, okay? So some of this is non-bonding. The number of non-bonding electrons, well, he doesn't have any little dots around him, so his is 0 minus half of the bonding electrons. So like in this, there's 1, 2, 3, 4, 5, 6 total electrons that are being bonded with him. So 3 minus 0 minus 3 is 0. So his formal charge is 0, and that's good. And then we'll jump over and we'll do chlorine. We'll do like this chlorine here. So chlorine is, we already said his formal charge was 7. And then he's got 1, 2, 3, 4, 5, 6 non-bonding lone pairs. And then he's got a total of 2. And so that gives us 7 minus 6 minus 1, which is 0. So the formal charge on the boron is 0. The formal charge on the chlorine is 0. We don't actually put them on the structures. Just be aware when they're 0. Now, if it had been a +1, then we would put it like that. And that's really, again, it's for organic chemistry. I'm telling you this more so. But it's we'll put a +1, or maybe we'd put like, if it was a minus, it would be a -1. But you put a little circle around it. Because it's not a real charge, it's just a charge. Now that formula might feel a little weird, or it can be simplified, and it can be simplified. So this is what formal charge is really checking. It just wants to know if what they have matches what they came with. So matches what they should have. It's like, what do you come to the party with? So as long as the number of electrons that it came to the party with if you still hold on to that exact same number in some form or fashion, then it's going to be 0 and everything's going to be happy. But if someone shoves an electron in his face or someone takes an electron away, well, then we're going to have some issues and the formal charges are going to start getting off. So for boron, again, that's our valence. The should have is the valence. Boron should have 3. He should be coming to the party with 3. And then the number that he actually has, I'm going to zoom in and I'm going to make this a little bit more of a dot here. So in that bond, the boron has 1 of each of the electrons in that bond. So he's got a total of 3. So his formal charge is 0, which matches what we figured out up here. So that's good. And then for chlorine, what should he have? I switched to blue on this one. So chlorine, he should have 7. That's what he comes to the party with. And then we look, we've got 1, 2, 3, 4, 5, 6, 7. Yay, that's also 0. So these two structures I'm doing the examples for, they do both come out to 0. I use the H intentionally because H is always going to be 0 because he's just got the one thing that he's bonded to. H comes to the party with 1. He's got one thing, he's always 0. And let's check the oxygen. So oxygen comes with 6, and he's got 1, 2, 3, 4, 5, 6 things attached, which gives him a formal charge of 0. So these are all examples of things that have a formal charge of 0. I'm going to jump down here because this is an example of different ways you could draw a carbon with 2 oxygens. So if you look at these, and you were to add all these up, these all have the exact same number of electrons, they have the same atoms, and these are all different ways that can be drawn. Let's practice our formal charge to see if we get 1 for this one. So oxygen, it comes to the party with 6. And it has 1, 2, 3, 4, 5 things attached to it. So look, he comes out to be positive 1. And we'll check this oxygen over here too. It comes with 6, and this one has 1, 2, 3, 4, 5, 6, 7 things. So he's negative 1. So formal charge tells us between these 3 structures, we want the structure where all the zeros is best. Yay, it's that one. If we had to choose, if we didn't have that one as the option and we had something else and we'd had to choose, then this would have been better because it was all ones. This one is just bad. If you get a 2, it's really, really bad, and there are probably different ways of fixing it, and you just haven't thought through another way to draw the structure, making more double bonds or triple bonds or something like that. So that's how formal charge works. We're going to do a lot of practice. Make sure that you're getting your formal charge correct.